firstly, you never have to apologize. No guest has to apologize on this channel for being technical. The audience loves the technicalities, and that's in large part what separates this channel from others.
Yeah, okay, then I'm glad to hear that. Of course, still I'm hesitating. I mean, let me just, I don't know if the audience is familiar with the measurement with the measurement problem in quantum mechanics.
Okay, so why don't you outline the measurement problem? But also, I'm still confused as to how you get the squares, the psi squared instead of some other nonlinear term like psi cubed or psi fourth or what have you. Explain that to me.
Yeah, okay, good question. I mean, this is because this conserved quantity you get is kind of sesquilinear in the wave function. This is what you get from the mathematics.
Uh-huh.
And well, of course, ultimately it has to do with the fact that I start with the Hilbert space in the first place. I mean, I start with the Hilbert space. I mean, one of the basic ingredients of a quantum thermal system is a Hilbert space, where you have a scalar product already. And then this scalar product can later be represented in spacetime with the surface layer integrals. But the fact that it's still sesquilinear comes from the original Hilbert space scalar product.
Sure.
But still, it's kind of interesting that all these conservation laws and so on fit together. I mean, this kind of, it gave me like a kind of confidence that we are on the right track. I mean, that what we are doing really makes sense because somehow you see that the structures you get is really what you need to formulate physics and so on.
Sorry, you say we here. At what year was this and who is the we that you're referring to?
Yeah, okay, good question. I mean, this commutator inner product, this is maybe 10 years old. So, I mean, this is in a paper together with Nikki Cameron and Marco Oppio. So Marco Oppio was a former postdoc of mine who unfortunately dropped out of academia a few years ago. Nikki Cameron is a collaborator of mine, and we work together since, more than 25 years. So he's a regular visitor also here in Regensburg, and also he's in Montreal at McGill University, also visit him there often. So, I mean, we work together since many years. And, well, I mean, as I said, I mean, so this commutator inner product is not so old, maybe 10 years old.
You have another book that's like almost 20 years old, The Principle of Fermionic Projectors or Projections, if I'm not mistaken. I've been studying you for quite some time now, so I'm getting many of these ideas mixed up. And I know that we have to get to the dynamics of space-time as well as the measurement problem. Why don't we get there?
Okay, fine. So maybe just summarize the measurement problem. So, I mean, if one does a measurement in quantum mechanics, then this also changes the system. I mean, and then mathematically one computes the expectation value with respect to an observable. And this tells me about the expected outcome of the measurement. And as a result of the measurement, the Hilbert space vector ends up in an eigenstate of the measurement apparatus. So this means depending on what you measure, also the system changes and the state vector ends up in the corresponding eigenspace of the observable. And this is something which doesn't have a good explanation within quantum mechanics. I mean, the standard Copenhagen interpretation of quantum mechanics, this is one of the postulates. But this is nothing which is explained intrinsically from the equations of quantum mechanics. It's nothing you can derive from the Schrödinger equation.
Mm-hmm.
In fact, it is something extra. So this means when you do a measurement, something happens which cannot be explained within the theory. And this is not a fully convincing. I mean, this is not convincing. And of course, this has puzzled physicists for many years, and there are different approaches to explain that. And now this causal Fermi system approach also provides an answer, but in this case, it is really a consequence of the dynamics as described by the causal Fermi system. So you don't need to put this, I mean, people call this collapse of the wave function or reduction of the state vector, so that the wave function kind of changes in the measurement process. And this is something which can explain from the equations coming out of the causal action principle. So this is something we just wrote last summer, so this is really fairly recent. And this also answers the question with the Born rule, which kind of started our discussion here.
I recall your solution to the measurement problem has to do with noise.
Yes, exactly. So, okay, I see. So you looked at the paper in more detail. So the way it works more is as follows. So
I do my homework.
No, okay. So let me try to explain this. I mean, so we have this Euler-Lagrange equation of the causal action principle. So these are kind of the fundamental equations. And then, of course, as a mathematicians, we want to know how do the solutions look like. And I spent quite a lot of time analyzing the solutions of the Euler-Lagrange equation and of the linearized Fiet equation. So this is a linearized version of these Euler-Lagrange equations. So I studied this in detail. And it turns out that there are many more solutions as you would expect from other physical equations. For example, you get the solutions of Maxwell equations, like say plane electromagnetic waves. So these are specific solutions, but there are many more. And then the question is, what do all these additional fields do and how can you describe them? And our approach is to describe them stochastically. So this means we say, well, we don't know how all these fields look like. And the reason that we don't know how they look like also has to do, we don't really know what the microscopic space-time structure of space-time is. We just know how space-time looks macroscopically, but we don't really know what's going on very small scales. And these kind of fluctuations on small scales, they can also be described by these linearized solutions. So this is why we take the point of view where we have all this multitude of fields, which we assume to be non-zero, and we describe them in a stochastic way. And they couple to matter. So suppose you have an electron sitting here, then all these fields couple to this electron and also have an effect on the dynamics, on the time evolution of this wave function. And this is then something we studied in detail, and it turns out that one gets a connection to collapse models, which are already around. I mean, there's this particularly CSL model, continuous spontaneous localization model. So it has kind of similar features what we get here. And in this model, one considers the Schrödinger equation plus a stochastic term plus a nonlinear term. So it's important to have these two types of correction terms. And now our stochastic terms, this comes from this background, which we describe stochastically, as I just tried to explain. And the nonlinear term comes from the fact that the causal action itself is nonlinear. So the resulting equations are nonlinear equations. So therefore, we have all the ingredients right there. And we saw, okay, it really gives rise to such a collapse model. And I should also mention that it's not exactly the CSL model. The model we get is somewhat different, which has to do with the fact that everything is kind of non-local in time. I mean, I also already explained this surface layer integral where everything is kind of, you integrate over a small time strip. There's something similar in the equations as well. Things are kind of smeared out in time, and this gives like an additional feature of the model, which also seems quite important and interesting.
So the way that you get it is via reproducing the CSL model?
Yes.
Right. Okay. Now, just for people who are interested in different interpretations of quantum mechanics, I'll place a link on screen here because I have a Substack where I go through the top 10 most popular interpretations, even though they should in some ways be called different theories of quantum mechanics as they differ in their predictions. And the CSL is one that differs. So if my memory serves me correctly, there are two parameters, at least in the CSL model. One that has to do with the localization length and also a collapse rate. So do you have bounds on those?
Yeah, okay. I mean, there are you're right. There are two parameters in this CSL model which can be tested experimentally, and there are also tests going on right now. I mean, people are measuring these parameters, or in fact, right now one gets bounds for these parameters, so the parameters can only be in certain ranges. And then there's another, the effect which is, which puts the best bounds on these parameters is a heating effect. So then, if you think you have an electron sitting there and then it's surrounded by kind of background fields, one effect is that the electron starts wiggling, so the say energy from this environment, it's transferred to the electron, and this is then something one could measure. So more specifically, this is done for example, in this Gran Sasso tunnel in Italy, where they also do neutrino experiments. So you are in the middle of a tunnel under big mountains, so they're surrounded by rocks. So this means there is not much radiation. And then you just have a probe sitting there. And then if you believe in the CSL model, then there is still some heating taking place, which means that this probe then emits photons just spontaneously, which you could then measure. So this means one just puts a probe there, one puts kind of detectors around it to measure like photons of different energies, and then you try to find something. And this puts bounds on these parameters. And now an interesting feature is that for our model, this is something we are working out right now. I don't know if you want to mention this in the video already or not, because the paper is not finished yet.
Sure.
Right now we are maybe let's write it like that. Let's say it like that. Right now we are analyzing if our model also gives rise to heating.
I see. These are preliminary results. You're verifying them.
So it seems that our model does not necessarily give rise to heating. So this means that these experiments should not be, these experiments do not really test our model. But as I said, this is preliminary. Maybe you should even cut this out as you like.
So my understanding is that the CSL also has some violations of conservation of energy. And I'm not sure if yours would also.
Yeah, exactly. This is basically this heating, what I said, is also a violation of energy conservation, because then the electron, if it gets hotter, it gets the energy increases. And this is something we are looking at right now. And it seems that in our model, energy is conserved.
Interesting. I have a slew of questions that I'll get to more of them at some point. We should get to the dynamics of space-time.
Yeah, okay, fine. Maybe we should come back to your question. How do you get the Einstein equations, for example? What I explained already is that we get Minkowski space as a minimizer of the causal action principle. So this means we can describe a non-interacting space-time. Of course, this is boring, but this is kind of an important starting point, because now we can put in a dynamics to the system. So we can, for example, introduce electromagnetic fields, introduce additional particles, antiparticles, gravitational fields, and so on. So we can consider any space-time, no matter, it doesn't need to satisfy the usual physical equations. We can just take our space-time and add additional stuff. And then we can ask the question, does this new space-time still satisfy the Euler-Lagrange equations or not? And the answer is, in general, not. If you start perturbing the system, the equations will be violated. But then it turns out that if you consider specific perturbations, then the Euler-Lagrange equations are again satisfied. So in other words, these are the perturbations which are allowed physically. And then it turns out that in certain limiting cases, you see, for example, if you introduce particles, antiparticles, and a Maxwell field, then the Euler-Lagrange equations of the causal action will be satisfied if and only if the coupled Einstein-Dirac equations are satisfied. No, not Dirac, sorry. Dirac-Maxwell, of course. So if the electromagnetic field satisfies the Maxwell equations, and if the electrons satisfy the Dirac equation. So in other words, you get the dynamics of the usual physical dynamics back. So this is why, this is what we call the continuum limit. So on this continuum limit, one gets back the physical equations on the level of classical interaction. So we have a classical electromagnetic field coupled to a system of electrons. And with gravity, it works similarly. So we also get then the coupled Einstein, Dirac equations. If we introduce a metric and then ask the question for which metrics are the Euler-Lagrange equations of the causal action satisfied.
Okay, so if you can get the Einstein field equations from this approach, and also space-time itself is just via this emergent web of correlations. I don't even know if we want to use the word emergent, but you get the idea. I imagine that these are fighting words at a general relativity conference. So what is the technical pushback you receive when you present this to relativists?
Yeah, okay, good question. I mean, with relativists, in fact, they don't object to what I'm doing. I mean, typically, like relativists, they are interested in I'm talking about, let's say, classical relativists. I mean, I know them quite well because I also worked on classical relativity for quite some time. I mean, the classical relativists, the starting point typically is the Einstein equations. So we write down the Einstein equation, we have some meta distribution, and now we want to find solutions, we want to analyze solutions, analyze the dynamics, and so on. And then this is a problem mainly of solving PDE. So it's like a partial differential equation problem. And many people are mathematicians like me. I mean, they delve into the analysis of these equations, and but they often don't really care where the equations come from. I mean, it's just say where this Einstein formulated the Einstein field equation, and I want to analyze those equations.
Right.
So therefore, I mean, I have good contacts with many of these people, and I know them quite well. But typically, when I then start talking about causal Fermat systems, then I say, okay, fine. I mean, if you are interested in that, then go ahead. But I mean, I'm more conservative. I just want to stick to the equations I'm familiar with, and I just want to work on the Einstein field equations. So this is my typical reaction I see from this community. And of course, I mean, I understand this well. I mean, for me, one reason why I moved away from this kind of analysis of PDEs is that I really am interested in doing new physics. I want to do something which has the potential of going beyond the standard physical theories. And of course, this is why I pursued this causal Fermat system approach. And then there are other people to address. I mean, for example, I could talk to quantum gravity people. And I mean, they are, of course, more interested in what is the quantum nature of space-time, or with these causal set people, what is the structure of space-time on small scales and so on. But this is a somewhat different community. These are more like physicists working on gravity.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CURTJAIMUNGAL.org, kurtjaimungal.org.